An overview of integration. The notation for something that we call an integral is the following. We say this is the integral of f of x dx. But what does it really mean? Well, there are four main interpretations of the integral. And the interpretations overlap each other. But we will break them apart to see these different interpretations and also see some of the overlap as we go along. Couple quick notes. This notation is what we call an indefinite integral. And then if we were to write it something like this, where I have numbers on the bottom and top, which are called limits, we call this one a definite integral. And we'll see why as we go along in this video and or subsequent videos. But let's look at our first interpretation. By its nature, an integral is a summation of very small things. More specifically, of infinitesimally small things. It's why this symbol for the integral looks like a stretched out S. So we could have written an integral like this. It's kind of where we start when we're doing integrations. Where hopefully you recognize the symbol as being the summation of things. Now, what am I summing? Well, in this case, I'm doing a whole lot, look, from 1 to infinity, of something. Well, what is the something? I have a y value times not an x value, but a change in x value. Now, how big is this change in x value? It's incredibly small. So it is a summation of very small things, but in particular, a y times a delta x. That notation becomes a little bit cumbersome, which is why we change it to look like this. But when you see this, I want you to see it is a summation of very, very small things. Now, this interpretation that it leads to is really kind of a calculus 1 interpretation, but we can continue to think of this interpretation as we go into higher levels, but we just add some things to it. And so the second interpretation that we have is that it gives us an area, I'll put in quotation marks, an area, actually I'll put everything in quotation marks, under the curve. So this is the way we say it. The area under the curve. Now, what do we mean by area under the curve, especially since we're in quotation marks? So I'll draw a function, just a very simple function, call it f of x. Now by area, why I put it in quotations when I start, is because it's really a signed area. And a signed area means it can be negative. So we have to be careful when we say area, because a physical area is always positive, but an integral quote-unquote area can be negative. And then I say under the curve, that's the way pretty much everybody says it. We don't really mean under the curve because under the curve is forever. What we really mean is between the curve and the x-axis. So we're talking about, for example, here to here. And I'll call this point A and B, which, as we'll see later, are our limits. So how does part 2 relate to part 1? Well, notice that if I made very, very small rectangles, I'll draw just a few and I won't make them very small. I'll make them big enough so we can see them. Like this. What is the height of each of these rectangles? Well, the height of each rectangle is f of x. And the base of each rectangle is delta x. And if we are to add all of these together and we let delta x get really small, this equals the area. And as stated, as you go forward, we can use an integral to find other things that we call measures, like length and volume and surface area and all sorts of other things. But for now, we're going to think of the area under the curve being rectangles. What is the third interpretation? Well, the third interpretation of an integral is that it's an antiderivative. So how does an area under the curve give an antiderivative? I'm going to do a very simple example here. Not a proof, but just to try and convince you that it's true. And I'll draw part of the line y equals 2x. And then what we're going to do is we're going to find areas on an interval. So let's put an interval. Let's say 0 to x is my interval. And then I'll put area next to it. And let's see what happens. So on the interval from 0 to 0, the area beneath the curve is really an area at a point, so there's no area. How about on the interval 0 to 1? Well, on the interval 0 to 1, I know that we got rectangles up here. That's really theoretical, as we'll see when we do something called a Riemann sum. But I can use geometry to get this exact area if I need to. And notice that we have a triangle whose base is 1, whose height is 2, and whose area is 1. How about on the interval 0 to 2? Well, on the interval 0 to 2, now we have a bigger triangle whose base is 2, whose height is 4, and whose area is 4. On the interval 0 to 3, we get an even bigger triangle whose base is 3, whose height is 6, and whose area is 9. Without drawing it, because I'm out of space in my picture, but you could easily confirm that on the interval from 0 to 4, the area beneath the curve is 16. So what is the area on the interval 0 to x? By pattern, we see that the area is x squared. So that the area under 2x dx is x squared. Now I did a definite integral, but later on we're going to put a plus c. But just for now, I'm just trying to convince you that, at least in this example, the area beneath a curve gives the antiderivative, because the derivative of x squared is 2x. One final main interpretation is that the integral is an accumulation or an amount of change. A derivative is a rate of change, an integral is an amount of change. And I will try to convince you of this algebraically here. So I'm going to do the integral, not of f, but let's do the integral of f prime of x dx. And I'm going to change some of my symbols. Let's say that's the limit as delta x goes to 0 of what? Well, f prime of x could be written as delta f over delta x, as delta x goes to 0, times delta x, or df dx times dx. But notice what happens here. And now I'm going to put some limits on here. So let's go back and put some limits. So I know where I start. I'm going to start at x equals a. That's what the symbol means. And we're going to end at x equals b. So what do we end up with over here? Well, once again, we see that the antiderivative of f prime gives us f, doesn't it? Like it did just above. But also, if we understand the notation, this here is a summation of what? Let me cross these out to get these out of my vision. Well, this is the summation of delta f's, where I start at x equals a and end at x equals b. So just kind of briefly, if I had a to b, like I could have a tiny delta f, then another tiny delta f, another one, whatever, something like this. And that I end up with the total change in f, right? If I have the sum of a lot of small delta f's on the interval a to b, then when I add them all together, I get the total change in f on the interval a to b. Well, how do I find the total change in something? Just for a simple example, let's say I started at 2 and I ended up at 12. How do I find the total change there? Without thinking, you probably did 10, which of course is 12 minus 2. So the total change of f prime, that is the integral of f prime on the integral a to b, equals what? It is the total change of f on the interval a to b.